Colleagues, ladies and gentlemen, I'd really like to welcome Professor Hazel Faulkner.
Well, hello to all of you. I'm absolutely thrilled to see so many familiar and very close friends here today, so thank you all very much for coming. Well, my talk today is called Getting Considerably Wetter, and I think it's true to say that we are obviously quite in wide consensus now about the role of climate change in the future of the planet. In fact, you've only got to click on YouTube to find scientists like the well-known Al Gore talking to us in very clipped ways about the inconvenient truth about the planet's greenhouse gas envelope, increasing the warmth near to the planet, and how that is causing the warming up of the oceans and the melting of the ice caps, and possibly leading to cutting down of the thermohaline circulation that's in the North Atlantic, bringing down those jet streams, and perhaps giving us some explanation for these wetter weathers that we're experiencing now, and possibly even some of the floods that we've seen in the Elbe and the Danube just this week. So there is a consensus and a big debate. In fact, there's a huge amount of material on the internet of all sorts, and what I wanted to do was to spend a little bit of time thinking about how the scientist who tries to make this information available and accessible is sometimes overtaken by Hollywood, who argue that the global ice caps are going to basically overcome the Himalayan mountain range, and to the bewilderment of this monk here, and leading to the destruction of civilization as we know it today. And so, of course, that's just fun, and that's one translation of science. But, you know, usually in those disaster movies, there's a clip in the middle where the scientist tries to communicate with a professional or the military about the extreme nature of the science that's facing the planet. And I couldn't find that clip, unfortunately, so I've mocked one up. And here we have the scientist, obviously, on the left with the beard, shorter, glasses, and saying, you know, the climate change is faster than we predicted, Jed, but the politicians just won't listen. And the politician paid by Robert De Niro says, oh, sure, your goddamn science boffins are always getting it wrong. So this is, you know, quite an interesting exchange for me, because what's happening here is that the scientist has increasingly realized that there is an uncertainty envelope in the work that he's undertaking. He's trying to communicate it in a very constrained time setting, which for those of us who work in flood risk management, we understand very well. And the professional is not receiving the information in the same way as it's being transmitted. He has got a different agenda. Maybe it's political, maybe it's inconvenient, as Al Gore would say, or maybe, you know, he wishes to get into some sort of litigious relationship with science. And so there are lots of ways in which this relationship is represented and issues to do with this. And it's not a trivial point. The scientist was a seismologist working in Italy, and the guy on the right was a politician. He would have clapped the guy in jail. And I think you've probably seen this article in which scientists failing to predict earthquakes properly in relation to the Archaea earthquakes, instead were asked to take the burden of responsibility for the science to be uncertain, or this uncertainty in the science, and the responsibility goes straight back to the poor scientists, and they're still in jail now. So the presentation looks at not so much getting considerably wetter, the change of the planet from possibly conditions now to a more wetter scenario. We know that story. I'm interested really more in the way in which the science is translated within the policy and at the professional interface. And it's a huge issue, of course, because there's a lot of material out there about the public understanding of science and the way in which scientists have various agendas and so on. So I want to personalise it, if it's okay, with the audience and talk about the issues in two contexts, in the context of the soil science areas where I've worked and in the context of flood risk management more recently at FHRC, Flood Hazard Research Centre. Now, the two pieces of research that I want to draw upon, the first one is this piece of soil erosion hazard research, which I undertook with the British Academy's funding with the CSIC in Spain and with a lot of help from John Boardman, who I can't quite see where he is at the moment, but he's there. A lot of support from Oxford University's Environmental Change Institute, a long-standing friendship with John there, which was a really interesting piece of work, and I'm sorry in advance, John, for boring you with it because you know it already. And then the second piece of research, which I undertook in conjunction with the EPSRC research-funded Flood Risk Management Research Consortium, and again, there's somebody in the audience to whom this will be boring as well. Gary Pender is here somewhere, and Professor Gary Pender from Heriot-Watt University. He's not waving his hand, but he's there. And we undertook a very interesting risk translation exercise at Met Office in a few years ago in relation to risk communication during constrained time period during a flood. And because it was fun and it was interesting, I'm kind of keen to put that into my program as well today. So the scope of the presentation, well, obviously, I'm going to, at my own inaugural, going to make a very personal story, so some sort of a timeline running through the presentation, showing how my thinking has changed from 1972 to 2013. And as Jan very kindly introduced me to you, as someone who started very much from an arid land geomorphologist, moving into flood risk management, which obviously makes me get considerably wetter myself. And obviously I also moved from logical positivism across to a much more nuanced, post-normal, social science engagement model of thinking. And I'm not saying anything about whether that gets me wetter. Anyway, leave that one to just drift off. The content then contains the challenges of environmental science and some of the paradoxes that exchange introduces. And the paradoxes don't only include the idea that, oh, it's getting warmer, but it's going to get nastier. It includes much more interesting paradoxes, such as the more we know about science, the more difficult it is to communicate because of the uncertainties and the non-stationarities that we have to face in the future. First of all, then, very early days, and I was really delighted to see a group of people here from North London Polytechnic, colleagues here in the second row with whom I worked for many years. And many. And they're still talking to me, so this is good. This is good. And really, I would have said, and I think they would have agreed, that I was a physical geographer, taking this idea of understanding the environment very straightforwardly, thinking that we can understand how the environment works, then we can predict what will happen, that the science has within it the potential to predict forward and to find and form solutions. And the sort of thinking I had in those days was that soil erosion and flooding are increasing. We've got these vulnerable soils, and agriculture is making some of the soil settings more vulnerable because of land clearances or different land use practices, and that might lead to changes in flooding and pollution loads, and so that the advice that we might give about soil loss would be useful. Some of the on-site effects that we looked at were soil erosion loss from plots, erosion plots, and the discipline moved quite a lot into the off-site effects thanks to the work of John at the ECI, who looked very particularly at the off-site effects of muddy floods like this, which are caused by erosion on fields. This one's in Oxfordshire, but lead to contamination of rivers containing streams. We thought, I think, I'm sure John would agree, because when we went to these corporation science and technology meetings very frequently in Europe towards the end of the 1990s, there was an assumption that we have 50 years of soil research to use. We've got modelling, monitoring and management literature based on that science. Prevention is obviously proactive, sound theoretical basis for management. This is the logical positivist mindset here. And if you do cost-benefit analysis, these show that soil conservation pays on all fronts. So farmers will obviously be rational and will seek to minimise soil losses on that basis. And additionally, because we were talking to engineers as well, we have the technology. We might have a slightly over-egged solution here to soil erosion. Might say that was slightly over-engineered. And certainly one wouldn't want to solve soil erosion problems like that as a general rule. So we were thinking of using the models to generate vulnerability maps, identify hotspots within the environment, and increasingly using GIS, nested GIS systems to do this. That would give rise to hazard maps that could be utilised in interface with professional farmers and with transfer extension services within the soil management professional group. But, you know, it was clear to me after 25 years that soil erosion is still a serious issue. And so a lot of us were starting to ask, what are the reasons for soil erosion continuing on the scale that we see it in the UK, but also particularly in areas like Spain and in other settings where desertification and land degradation are accelerating at a continuing and rapid pace. One explanation might be that the science might be wrong. First thing you could think about, perhaps using plot scale data, putting a plot on the ground and working out how much soil is lost from that plot and then multiplying it up for the area that's bare land and saying that's how much soil will be lost. That plot scale and that scaling up is inappropriate when you've got, this is a sort of plot scale, this is a little silly piece of research that a friend of mine did at Hertfordshire. I knew you'd like that, Leah. Showing that if you change your land use from plain to mulched to vegetation, you get better water than if you don't grow anything on it. So this is the sort of rather silly plot scale finding that scientists had in many settings being scaled. I'm not saying there weren't much more complex algorithms, but there had been a tendency not to look at spatial variability. And so the group of us that started to look at rills and gullies started to say, really, in this landscape, the soil is lost from inside that gully and in those rills, and you can't really use plot scale arguments in this type of setting. And so increasingly gully erosion models, rill initiation models were starting to be developed, but not really getting themselves all the time into management tools like the the universal soil loss equation, which basically is a scaling up for things like bare area and land use and so on. So we knew how these systems worked more or less, but it was getting it into management literature that we thought perhaps wasn't working. So that's one possible explanation. And you can see on this field, very good example, this is in Belgium near Leuven, that the soil loss is indeed from inside the system and not from the surface. Second example of why the science might be wrong comes from my work in the Mediterranean environment. This is not a very good photograph, but it's a photograph of a dendritic gully system, a system generated by water flowing over the surface, gradually accumulating the flow into bigger and bigger rills and gullies. And that is very easy to model on a computer, extremely easy, and it was very attractive to generate models like this, which were the ones supposedly leading to rill and gully initiation. Now, in the Mediterranean context, this doesn't really work in the badland settings where I have worked. And have I got the group from Chester here? A group of students who I met in the field with a colleague of mine, Roy Alexander 10 days ago in Almeria, who we spent some time looking at these pipe systems, and I think it was very obvious from the work that I've done in these pipe systems that you're not generating soil loss from the surface at all. The water is getting into the ground, it's developing a relationship with the dispersive clays there, deflocculating them, leading to macropore and pipe development. These can be invisible on the surface, and only when the roof collapses do you have any idea the volume of soil loss that's come from these sorts of gullies. And so again, if you're going to assume that the soil is coming from the surface and therefore put these little walls in to stop the surface erosion, but in fact you've really got piping developing in a dispersive soil setting, you will end up with these big gullies that cut right through the existing terraces. So, the science in this setting possibly wrong in a waste of time to put these very expensive terraces in when the real mechanism on certain materials is very different. So, there are examples where you could say our understanding of soil erosion is still flawed technically. I hope Ian doesn't disagree with me too much there. I'm a very well-known soil scientist sitting right in the middle here, so it's a bit worrying for me. In the UK, I started to think about policy change. This is to do with the work that we did with COST, Cooperation, Science Technology work with John Boardman, again encouraging us to join up as a group of scientists working on this idea of soil management, soil loss. And John's written quite a lot of papers, and I do hope I'm not misrepresenting. I certainly didn't do the work in Lewis. That was John who did the work in Lewis. I'm sorry about that. Don't know whether I've ever claimed credit for that, but I don't think I did. I don't think I did ever claim credit for it. This is a piece of research that is entirely driven by John's knowledge and knowledge based. But he started to look at where soil loss was in terms of policy shifts. And this is one of John's photographs of a colleague, a soil farmer, just to show that on very shallow soils on the South Downs, that common agricultural policy was encouraging farmers to put wheat in at times of the year where the heaviest rain came, and this was leading to an acceleration of erosion, so a policy-driven increase in soil erosion. Again, in the Mediterranean, this is more work that I did, we looked at that. This is the area you students were at last week, where we were looking at these traditional terracing systems, only to find that they'd been completely eroded through by the piping. And in this landscape, the farmers are clearing their landscape hectare by hectare in a huge very rapid rate, because of being given subsidies for clearances. And these subsidies were related on a per hectare basis, and often were being cleared on soils that the farmers wouldn't normally, in their normal mind's eye, want to really manage, because they knew it eroded very quickly. So we had this sort of clearance in the same landscape that you've just seen now, that was traditionally being managed with the little terraces in the headwaters, farmers clearing huge tracts of land for these kind of linear olive and almond plantations. And so this led to myself and several of us thinking about the way in which the Common Agricultural Policy in its first phase, in its first incarnation, had not really helped land and environment management at all, particularly in these two examples that I've got here for you. So those are the hypotheses that I would have had up to 2006, and when there was the new European legislation brought into or proposed in 2006. We started to think, why was the science not really converting effectively to management? And John Boardman and myself and some colleagues in Spain had the idea to investigate whether or not there were some aspects within the farmers' livelihoods that were constraining the farmer from engaging with the issue of soil management. So this brings me down to this role of science in management of the farmers' livelihoods in two settings. And this is the piece of research I mentioned earlier. It was nested within the CAP reform idea. The CAP reform idea was that maybe subsidies could be given to subsidise conservation agriculture initiatives rather than to subsidise crop production. So that was the reforms of CAP, and we knew already that that reform would, if it was delivered effectively on all the European countries, would be a much, much better way of encouraging farmers to manage the land sustainably. So what the idea was that we would take the South Downs setting, which I've already shown you pictures of, and the Almeria, southeast Spain environment, again, those two environments, and do some hazard mapping. We took an expert system, an algorithm, which was based on the idea that soil vulnerability was spatially variable in relation to a lot of risk-associated factors that we could put onto layers in a geographical information system, and we produced complex maps of these two areas, the South Downs, beautiful South Downs there, and this same area I've just mentioned in southeast Spain. Okay, now I haven't got enough time because I want to talk about flooding as well, so I haven't really got enough time today to talk about the details of how we did this. It was quite sophisticated. We ended up with a very nice map. We found that the one on the South Downs even matched perfectly with some of the gullies that John had mapped following a rainfall event some years earlier. So we were satisfied, really, that these relative vulnerability to erosion maps were very useful and were predictive of erosion. And the experiment was this. We wanted to trial these formulations of how the scientists saw the risk of soil erosion, so a scientific version, a scientific prediction, to see if it would be recognised by the farmers, found useful and embraced by them in these two different socio-economic and cultural settings. In order not to introduce the idea of the soil erosion to them too early in the interviews, we asked the farmers, I don't know if this is ethical, it probably isn't ethical now, but we asked the farmers, what are the components of a sustainable livelihood for you? And we had 20 to 30 farmers in Spain and more like 40 in the Downs. And the question, the interviewers, who could speak Spanish and English, were asked to introduce soil only latterly in the debate if the farmer hadn't mentioned soil erosion as being a concern in his livelihood and in his aspects of role as a farmer. And then we transcribed the interviews and made some solutions and findings from that. Well, the first thing that we found, and here's the unisex farmer here sitting in the middle of his decision space, surrounded, and this is not a new diagram, I know, because other people have said these same things, but sitting outside the farmer's perception of how he sees his life, we found that the science was sitting way outside here, that our map didn't, in Spain, it didn't interface with the farmers at all. In fact, the interesting finding was that for most of the farmers in Spain, the idea of a soil was not really very interesting to them. They were interested in water and land. Suelos is a scientific word meaning soil. They never used the word suelos in the interviews. So the farmers were only getting the scientific translation via these conservation guidelines which were being produced locally by farmers groups. So inasmuch as we had produced something of use, no, it wasn't of use. It was not declared to be of any use. In fact, they didn't really read the map very well and didn't find it at all useful. We had identified their farms and everything on the maps, but they were not really thought to be useful. I mean, it might be just that a female Northern European English-speaking academic telling them that they need to have this map is, not the right thing to tell people. I don't know. Could go down badly. But I didn't really kind of think of that at the time. But the other... And the girl doing the interviews, the Spanish girl, was very beautiful and Brazilian, but still didn't engage with it very much. So the cultural background and personality and lifestyle issues which drove how a farmer understood himself, if you like, his epistemological context, altered how he perceived the risk of his life, and the other things that sit on the side here, the socio-economic, not the physical, but the socio-economic issues of legislation, other enterprise opportunities outside the farm, common agricultural policy. These economic vulnerability issues were at least as important to him as issues of soil fragility or vulnerability. So this was a finding in Spain. In Sussex, the farmers were really interested in the maps. In fact, they were very interested in the maps, and they told us where they were wrong. So that wasn't really helpful. They felt that the maps would be useful if planners were making some decisions about what to do in the area. They didn't themselves feel that they would use the map, although several asked for copies of the soil erosion map so they could put it on their wall, that it was interesting. There wasn't one who felt that it would be an added extra value to his livelihood, but there was definitely a much better engagement. So, soil science, it interfaced in this experiment, this little piece of social science, only very obliquely with the farming in Spain, but much more in a different setting in the UK. One could hypothesize that this is to do with the fact that soil is very much valued in the UK. The relationship between the nutrients in the soil and the crop is taken as read in the UK. In Spain, farmers are using very thin soils. They're putting hydroponic systems into pipes which feed nutrients to the plant directly. So there's nothing really that you could call a rich sort of fudgy soil feeding the plant. So that might be some sort of explanation of how soil and soil erosion is not considered to be an issue in an area known for its extreme land degradation. So we have this paper that came out around about the same time, which I loved. White, Cates and Burton's paper, Knowing Better, but Losing Even More, the knowledge of the use of knowledge in hazards management. And they were saying something very similar, that some sort of social or socio-cultural information needs to be introduced into science when it's translated, and if we don't do that, it's not really going to work as well as we might. Now, perhaps it's very obvious to everybody, but having come from where I was coming from, this was quite a thing, really. So here's the summary from the soil erosion research. It could be the wrong science. It could be the wrong science applied at the wrong scale, or measured at one scale and applied at another. It could be that policy is overriding good science in the case of the first pillar of CAP reforms, or that the science only really works in certain cultural contexts, and perhaps our scientists are misunderstanding what a problem is from the point of view of people who live in different environments. I was reminded, incidentally, of that sketch in the Monty Python film where he goes to ask a group of French soldiers if they will join him for a quest for the Holy Grail, and they just look over the turrets and say, "We already got one." So, we already got soil science. We don't need you to come and tell us. So there were some issues of how we did it, which might have been part of the answer. Well, luckily, the Common Agricultural Policy has decoupled agricultural subsidies from production, and we're hoping, and the jury's out now, that this is going to lead to all sorts of good and new initiatives in relation to cross-compliance. I know Mary here has done some work on the policy, no, she is, but on some of the policy instruments that are relevant here, and so it looks good, really, that EU is now looking much more sensibly at these two things, agriculture and soil management. So we come to more recent times, flood hazard research, and this was a bit of a culture shock for me. I remember at the going away party I had at Kingston, Stuart will remember me saying, I'm a bit worried because, I'm an old dog and they're going to expect new tricks. And it's certainly true, new things were expected, because I was starting to work with a group of social scientists, people who didn't accept at all, as I did, that flooding was generated and could be understood entirely in physical terms, and therefore could be managed in entirely physical terms too. And so we started to think about how flood knowledge could be translated at the professional interface. The sort of questions I was being asked to think about, have we got varied conceptualizations of the term risk? How can we unpick this? It's understood differently by different groups of people. If we have a problem, an environmental problem, is it risky because we're frightened of it, or is it risky because we can predict that the risk will become hazardous, and we can map and predict the sort of outcomes that we can do? So this is how I had been thinking and where my mindset started, and this is where the social scientists at the Flood Hazard Research Centre were thinking and working, and it was very interesting for me indeed, and quite hard actually. I had to understand too that there were sorts of uncertainty, and this was a big debate going on around this time, the non-stationarity of the climatic signal. If you have a non-stationary environmental sequence, you can't take half the data set to develop the model and then use the other half, use that model to predict the other half to validate it, because you can't assume that the signal is stationary. And in fact, model validation is under, in my opinion, quite serious pressure and constraints now because of not really being able to use stationary environmental series. So instead, scientists are getting into articulating really clearly the uncertainty of all the possible range of probable futures for a certain set of environments. And so uncertainty suddenly starts to be a very big part of the science. I mean, from the scientist's point of view, uncertainty it's there in the variables, it's in the monitoring, it's in the algorithm that you choose, it's in the assumptions you make, the scaling up that you, all these assumptions become sources of uncertainty and unproblematic from the scientist, but he's able and can express it probabilistically, possibly by bar charts or more sophisticatedly within erosion ensembles and things like that. Whereas from a professional point of view, you're not really interested in uncertainty because you've got to either do something or not. So actually, the uncertainty in the science, willingly passed over by the scientists, if you ask, is not really, it's inconvenient. As Al Gore said, it's not suitable information in an environment where binary choices are what people have to do, and where their professional agendas and missions constrain their time they have to embrace this amount of science. So I was being asked to look at a setting, Jim Hall says stationarity is dead, so we can't assume stationary series. We've got to look more at uncertainty and embrace it. Lots of papers by Jeroen van der Sluis, rather a suitable name for a hydrologist. And looking much more into the very difficult red material from the green area where I've spent most of my life, from this fairly certain assumption of fairly certain that we've got it right, and if we get it wrong, well, it's not really a big deal, to situations in flood risk management where the uncertainty is quite considerable now, and where the stakes, the decision stakes, are high. So we move into this setting of what they call post-normal science. So what does this mean for things like the normal translation tools that flood risk managers use? We started to talk about this sort of map. You're probably really familiar with this. You've probably Googled your own house to find out whether you're living in a 1 in 1,000 chance of being flooded area, or a 1 in 100 chance of being flooded area, and these are available on the internet. And the issue is, of course, if the series that we're using to develop the models that generate these maps are uncertain, then we have to articulate the uncertainty somehow in that map. For instance, the most uncertain positions on that map is on the line between the dark blue and the pale blue. That's the most uncertain, because we don't know if it's 1 in 100 or 1 in 1,000. The place where we're most certain is actually in the river itself. So maybe we need to actually dig down underneath these maps and have this knowledge is as valuable and as useful as this. So we have to, I shouldn't say that. It would be nice to consider the possibility that scientists would take the tool and embrace the uncertainty embedded in it. That was how we were thinking. So, I mean, there are people smiling here like Tim and Leanne who remember me having these, difficult conversations at this time because it's all very new material for me. So these questions came out in a series of papers that we started to write around that time. Jan, so the second example I want to give you is a little experiment we did on asking professionals to embrace uncertainty. And the thought that we had at the time was that this is a professional. And this is a timeline showing the high and low tides in Thamesmead. And the different colours on the line are time away from now. Now we know exactly that we're right. Pretty sure about what the tide will be like in 6 hours, 18 hours, 24 hours, so on. But as you get further away from now, your models start to diverge, and you don't really know which of the models that you've got are really going to be accurate and predicting. So these colours, this band of colour, is a measurement of uncertainty. And to me, I was thinking, well, if you have really nice graphical displays like this, you can ask perhaps professionals with the right translator, if you can translate this for them, and say, you can use this. This has got more information in it than somebody sending you a telephone call saying it might flood in 24 hours. This is more information for the professional than a simple translation tool. And I say this knowing that many professionals, when you ask them, want to just go, say, well, we don't want that. Just tell us what to do. It's all, you own the problem. You tell us. And I wanted to encourage a situation where both sides were embracing the fact that what was going on was uncertain, and that this carries more information than a simple telephone call to say, what we're thinking of is, you might have really high tides in 24 hours, but we're kind of not completely sure, which is how it had been for a while. So it was about this time that Gary Pender, who still is here somewhere, is hiding, who was the chair of the Flood Risk Management Consortium, suggested to me that as part of the consortium activities, we would undertake a simulation of a flood. The whole consortium would do this. It would be an exercise, an activity for the consortium, and it was done in 2006. And the intention of this was to simulate a flood on the Thames estuary. It took place at the Met Office in real time. So we acted out a real flood over a period of 4 days. We chose an event which was known to be associated with a high tide, a very high tide, and we imagined that we were 2 days, can't remember, sorry, 2 days perhaps, ahead of that. Oh, it's a 4-day period. No, we were 4 days. The prediction was perhaps 2 days. The aim of this was to explore a whole raft of modelling challenges that the professional engineers were working with. But from our point of view, the group of social scientists working with these physical scientists was to see whether or not we could use these simulations and these animated predictions to communicate to the professionals who might be involved in such a flood. And we wanted to think about the ownership of the uncertainty as it was passed around during the simulation exercise, and we also wanted to think about how the uncertainty was building up as models were feeding into each other during the exercise. So it was very interesting, and I thought you'd enjoy it today, so I've chosen it for this presentation. So it's located down here in Thamesmead. This is Thamesmead area here. If you notice this little wiggly line here, it turns up on some of the maps that you'll see in a minute. The lower, this Thamesmead area south of the Thames in that location. So that's the location that we're particularly interested in the flood risk management and modelling of. But obviously, to generate floods there, you have to understand not only the tidal system, but anything that's happening on the North Sea in terms of tidal surges, winds that push water up and build up on top of the event. And also, what was intended was to try and create an event that had a recurrence interval of more than 1 in 1,000, so a really very big perfect storm, if you like. And in order to do this, we had to put events on top of each other. So not just the high tide, not just the tidal surge, but in as well, a flood was generated, actually an event which had occurred in northern France that previous year, but we kind of modelled it as if it was occurring over the UK, and it was simulated as a real event, but not a northern France event. It was simulated as if it fell in the UK, and therefore contributed to the floods in the Thames. And additionally, we had some people modelling the Medway as well, because that comes in the Lower Thames area. And then on top of that, we had people who were modelling the fragility of the embankments to see whether or not the size of event that we were predicting would create the sort of load that would, break the embankments. And then we had modellers looking at to see if the breach occurs in the embankment, what happens to the flood as it runs through the Thamesmead area. Now that was the event. And these are the forecasters. The surge event occurred in November. A heavy rain event was one that had occurred in June that we used for simulation. The only artifice really was that the modellers arranged for the modest surge to synchronise with the extreme tide, and we translocated that heavy rainfall event. And obviously it's completely artificial to put them all together, but that was really the point of the exercise. So what were you doing? We invited a group of professional people who live and work in Thamesmead, an emergency professional, an authority planning officer, an environment agency risk manager, and the guy who lifts the barrier up and down. And we had them in a separate room. And what we did during the 4 days was, as predictions were being made and as the models were increasingly being ramped and put into each other, I was moving backwards and forwards from the modellers to the professionals saying, what are you going to do now? And translating the science and asking them about the utility of the science of the animation at that time in that, and they sort of bought into the whole sense of emergency, and I think we all kind of thought it was flooding by the time we'd finished the erosion of it. So this is big and messy, but I have to leave it up because it sort of explains all that we were doing. For a start, there's a timeline running down the side here, so that was the beginning of simulation, and this is going down towards the end of the simulation period. So the simulation process runs down the diagram. In the grey boxes are the data sources that are used to drive these models, and the RPA numbers mean research priority areas. These were the modelling groups that were there sitting in the different rooms at the Met Office. The very beginning of the modelling, all we have are weather data from the Met Office and some North Sea surge predictions. There are measurement devices in the North Sea that give you some idea of surge. That's a wind wave on top of just the sea, which is built up by the wind. And so those two models were used to simulate the North Sea water levels B. Now these yellow letters are where we had animations available. So right at the very beginning, we just only could show the professionals rainfall patterns. That's all we could really show them. But by the time the modellers had taken the surge and put it into this hydrodynamic model, which pushes the water up the Thames from the coast, so that's the Mike 2 series data, this model allowed the prediction of water level time series data at 38 points along the Thames. So that was simulated in another animated series of water movements and so on. That model then went into this overtopping and failure model. This is the one that looks at the defences to see if they're going to be broken by this type of physical process. And all these data obviously have to come into these models to calibrate them. And then we, having identified the breach and the time and when the water would be coming through, actually we had to slightly adjust the model because it actually didn't quite breach the defences, and we were so cross because we had really good inundation models for Thamesmead. We didn't really, we had to up everything a little bit to enable the which is good news. It's good news for us all. But in order to be able to trial all our modelling expertise that was present, we simulated a breach and allowed Thamesmead to be flooded, and ended up with a series of different inundation models from that. So on this diagram then, the pink is the series of modelling events, and the yellow, oh, here's the little Medway flood coming on in the side here, and the yellows were the tools that I had. These were my uncertainty tools, and a lot of them were couched in uncertainty language. Just a couple of examples. The storm surge data was presented to the professionals as a series of ensembles, Bayesian function ensembles, which generate. So this is basically a distribution of 24 possible futures based on running models a long time at a certain point in the future. And if you look at this look at these as a kind of a distribution, you see they converge on the fact that there will indeed be, it's too small to read, really be a big surge down the North Sea. So the translator, i.e. myself and Simon McCarthy, explained and interpreted these for the professionals and asked them if they would find this useful, more useful than just a telephone call or a traffic signal, yellow, green, red, which is what often people are communicated to in these settings. This is the breach. There's the little curly thing I asked you to remember, that curve, showing where the breach might occur. And this is a blow-up of the actual location of the breach. Don't let any terrorists see this. And here is an animation that does actually work on this computer for some random reason. And we had an opportunity to have the professionals say, what would you do if there was a breach here? And we also have animations that run with a timeline, with a clock running down the side of it as well. And so this was a really interesting piece of research on risk communication and the translation of uncertainty between science and professionals. And what did we find? I've got a lot of data points here, and it's boring to look at them like this, so I'll try and see what we found. The professional groups really enjoyed the exercise. They found the science quite easy to understand once it was translated by somebody who would explain what the simulation was actually demonstrating and what the limitations were on the modelling that had been undertaken. But it needed to be a conversation, and the personal touch was found to be very useful. At the beginning of the exercise, there was a lot of resistance to using complicated science, and they were mostly reporting that they couldn't use probabilistically formulated data, and particularly the gentleman who runs the barrier said, no, it's, if it's 38.3 millimetres, I keep them down. If it's 38.4 millimetres, I raise it. And there's no uncertainty, there's a rule. And so we asked him to think about how these data might help him to make a better decision rather than, a tick box kind of set of guidelines which weren't really based on an awful lot, really. So this was the sort of diagram I created. It's a timeline running along the bottom of our simulation. I was able to identify the uncertainties, moved like this. Obviously, as we got towards the actual event, the uncertainty of the modelling dropped considerably. The probabilistic nature of the estimates, so this is the physical modelling at the bottom, and at the top, where the communications were made with the professionals and the response groups in different positions in the timeline, because obviously if you're an EA environmental manager and you're a policeman, you have a different professional set of responsibilities at different points on this timeline. So we spent a lot of time mapping those as well. They enjoyed the fact that the uncertainty was decreasing as the time for the event approached, and they felt it was easy to understand once it was less uncertain. They didn't enjoy uncertainty in their jobs and felt that it was in need of someone else to translate, and they still felt uncomfortable about embracing ownership of the uncertainty. So the communication as well as the uncertainty envelope was a serious challenge for both the scientists but mostly from the point of view of the professionals as receptors. The ensembles were the most positively received. They felt they could understand those completely, and it has now been, in fact, Environment Agency good practice recently to introduce ensembles into exchanges with professionals at the emergency professionals, and also with people working on the site at the barrier on the Thames. There is a constant claim that people in professional practice want accuracy, and there is no such thing as accuracy in these contexts. There is simply a message with an uncertainty. It's a bit like having drugs in a box with, the contraindications. You have to buy into the uncertainty. You have to take some of the risk onto yourself in engaging with this. And it happens a lot in medicine, and there's a huge literature on this exchange between doctor and patient and so on, but not at all in the environmental field. So what are we going to do about this? I'm not going to read this through. Looking at these challenges, very different from the soil erosion ones. We've got a lack of stationarity. We have possibly difficult language, codified and distrusted language. Maybe there is semiotic or, semantic issues here. Perhaps the science needs to be more sophisticated. There needs to be some improved trust between the professionals and the scientists, and there needs to be perhaps a shared discourse, maybe in some neutral arena. Uncertain science is always unwelcome, and the subtlety of the uncertain tools is often lost in translation. So what did we do? We talked a lot about this within the consortium, and one of the main findings of the first phase of the consortium's work is that if you have people like our group who have engaged with your argument, local champions. So there's 5 guys who we talked this whole process through with in Exeter, went back and had a different look and take on science, and that is a result of the fact that we'd had this discourse or this translation experience. So those guys became local champions. Secondly, the tool needs to be matched to the communication interface very carefully, and there needs to be an understanding of each other's agendas and mindsets in order to match the tool to the exchange that's in question. And to adopt a neutral space for the conversations, and we suggested this translational discourse, which is a paper that I wrote in Ambio in 2008, I think. In which we talked about possibilities of a shared domain between 2 different groups, science here and planning, for instance, in which the conversations shown as lines are increasingly between domains rather than within the domains, and that this is actually possibly mapped out and becomes part of a discourse that the groups engage in. We've talked about and suggested between DEFRA and the Environment Agency the idea of virtual institutions, and we talked about the way in which the uncertainty tools could be embedded into decision making in the UK as a result of these types of piece of research. And Keith Bevan, who was instrumental in forcing me to think about uncertainty, and couldn't come because he's teaching in Uppsala, but so I'm quite glad really, because he would probably ask me a nasty question. We came to the idea that we could perhaps in time develop codes of practice which had joint promotions, joint tool development, and agreement over languages, communication goals and tools, the format language, and so on, none of which exists really at the moment. And so the toolbox development has happened. The Environment Agency are taking forward a group of uncertainty tools and tool guidelines. There's a wiki page, a sort of decision support tool being developed as a result of this. And I hope that uncertainty will increasingly become something that we have to embrace, and we do it with a different mindset perhaps than previously. So that's really all I have to say. I wanted to give you some examples of what science has meant to me and how I've had increasingly to embrace some of these issues that are to do with people's psychosocial and professional agendas, which hadn't really been part of my own personal discourse up to that point. So I hope you found it interesting.